It is October 19th, 2017. The time is 4:22 in the morning. The location is the summit of Haleakala, a dormant volcano on the island of Maui, Hawaii, rising more than 10,000 feet above the Pacific Ocean. Up here, the air is thin and cold, and the wind moves across the caldera in long, low sweeps that carry nothing but altitude. There are no city lights at this elevation, no ambient glow from the tourist towns down the slope. Just darkness and the sky pressing down with a weight that only feels real when there's nothing between you and it. The stars don't flicker up here the way they do at sea level. At sea level, you're looking through miles of turbulent, humid, light-polluted air. Up here, the atmosphere above you is thin and stable. The stars just hang there, sharp and still, like they've been pressed into black glass. Robert Wurick is working tonight. He's an astronomer with the Pan-STARRS survey, the Panoramic Survey Telescope and Rapid Response System, a project designed to sweep the entire accessible sky systematically, cataloging everything that moves: asteroids, comets, near-Earth objects that might pose a threat to the planet. The job is methodical. Most nights, it is profoundly, deliberately ordinary. You look at data, you flag candidates, you run software checks, you hand things off for follow-up observation. Nothing about the night is supposed to stand out. Wurick has done this hundreds of times. The system is automated. The telescope moves, captures images. The software compares them to previous images and flags anything that's moved between frames. He reviews the flags. Most of them are known objects, redetected as the telescope sweeps through familiar regions. Some are new detections, added to the catalog, noted, processed. Nothing special. Tonight is supposed to be like that. The telescope has already captured images of a faint streak, a dot of light moving against the fixed background of distant stars. That's normal. Moving objects get flagged all the time. Wurick pulls up the data, begins the standard calculations. The software has already identified it as something worth looking at, but that happens constantly. Everything worth looking at gets a second look, and the numbers don't work. He checks the velocity first. Whatever this object is, it's moving faster than any asteroid or comet originating from within our solar system should be able to move at this distance from the Sun. Every object in our solar system, from the innermost Mercury to the outermost Sedna and beyond, moves within a velocity range determined by the Sun's gravity. Like everything in an orbit, they have a speed limit imposed by the gravitational relationship with the Sun. Exceed that speed, and you're no longer bound. You escape. This object is moving at a speed that exceeds that limit, not by a little, by enough that the numbers are unambiguous. That's odd. But maybe the initial data point is slightly off. Maybe there's a measurement error buried somewhere in the pipeline. Wurick adjusts, recalculates with better constraints. The velocity holds. Then he checks the trajectory. An object moving that fast, on a path like that, its orbit doesn't close. It doesn't form an ellipse, doesn't loop around the Sun the way comets do, doesn't stay bound to the solar system. It passes through once, deflects slightly by the Sun's gravity, and continues outward on a hyperbolic path, a one-way trip. Whatever this is, it's not visiting, it's passing through. Which means it didn't originate in the asteroid belt, didn't fall inward from the Kuiper belt or the Oumuamua cloud, didn't come from anywhere within the boundaries of our solar system. It came from somewhere else, from outside, from between the stars. Wurick sits with that for a moment. He's looking at the first confirmed interstellar object ever detected passing through our solar system. The dot on his screen, roughly 85 million miles away at that moment, receding rapidly, is a visitor from another star system, something that formed somewhere else, around some other star, and has been traveling through the dark for millions or billions of years before entering our solar system. passing within 15 million miles of the Sun, and now heading back out into the void. He marks it for immediate follow-up. Other telescopes will track it over the coming days. The data will be checked and rechecked by multiple independent teams. The object will be given a name, Oumuamua, from the Hawaiian for a messenger from afar arriving first, assigned by the institute on whose mountain it was discovered. And then, as more observations pour in, as more telescopes point at that retreating dot of light, the questions will begin. Because it's not just where this thing came from that's strange, it's what it does next. Scientists had an explanation ready, the universe didn't cooperate. Welcome to Galaxy Pulse, where we go beyond the headlines and into the questions that keep astronomers awake at 3 in the morning. If you're new here, this is what we do. We take the mysteries that get a paragraph in a science journal and 500 words on a news website, and we sit with them. We turn them over. We look at what the data actually says, not what the press release says, not what the cable news chyron says, just the science, and the gap the science leaves open. If that's your kind of thing, hit subscribe. We put out deep space stories like this regularly, and the community here is sharp. Real conversations happen in the comments. Speaking of which, before we go any further, drop me something down there. Tell me what pulls you in more, the science that breaks down, or the mystery that remains after the science has said everything it can. I'm genuinely curious. I read them. Now, tonight, we're talking about Oumuamua. You may have heard the name. You may have seen a headline or two, maybe a Twitter thread from an astronomer you follow. Maybe Avi Loeb's name attached to something that sounded just a little too wild to be real. And I want to be straightforward with you right now. This is not a UFO video. This is not a conspiracy video. We're not going to sit here and tell you that NASA is hiding alien technology in a vault somewhere under New Mexico. What we are going to do is look at what the data actually says about this object. Peer-reviewed data. Observations from Hubble, from Spitzer, from ground-based telescopes around the world. And then, we're going to sit with the part that those papers, the serious ones, published in Nature and the Astrophysical Journal, cannot fully explain. Because, here's the thing, the mystery isn't in the speculation, the mystery is in the measurement. This is not just about a strange rock from another star system. That alone would be remarkable, the first interstellar visitor ever confirmed, arriving from somewhere outside the boundaries of everything we've mapped. That's already a story worth telling. But Oumuamua didn't just arrive, it behaved, in ways that don't fit our models, in ways that, years later, are still being actively debated in the scientific literature without a settled answer. And, by the end of this video, you'll understand exactly what those ways are, and why that one anomaly, that one number that wouldn't cooperate, turned a remarkable discovery into something closer to a genuine scientific crisis. So, let's start with some questions. What exactly was this object? Not in general terms, what specifically did we measure? What did we see? What made it unlike anything that had come before? Why doesn't the most obvious explanation, that it's some kind of exotic comet, actually fit the data? Why did it speed up, not slow down as it moved away from the sun, the way every object under gravity should? Speed up, faster than gravity alone allows. Why are serious, credentialed, peer-reviewed astronomers still publishing papers about this object years after it left our solar system, when by now it's billions of miles away and getting farther by the second? And here's the one that sits with me. What does it mean if none of our current models can account for what we observed? What does that actually say about the limits of what we know? This is not a dry textbook explanation. I want to be clear about that. This is real science, clearly presented, with the mystery kept intact, because stripping the mystery out wouldn't be honest. The mystery is the story. Stay with me, because what we find at the end might change the way you think about what moves through space between the stars. To understand why this became such a serious question for such serious people, we need to start at the beginning. We need to understand what scientists expected to find, and what normal, for an object like this, was supposed to look like. For decades before Oumuamua arrived, astronomers had theorized about interstellar objects. The logic was straightforward, even elegant. When star systems form, when a young sun pulls in a disk of gas and dust and begins building planets, the process is violent and inefficient in equal measure. Planets don't assemble cleanly. They form through collision and accretion. Smaller objects clumping together, occasionally catastrophically, over millions of years. And, throughout that process, the gravitational influence of the forming planets themselves throws material around. Some of it falls inward, toward the sun. Some gets flung into stable orbits. And some, quite a lot, actually, gets ejected entirely. Launched out of the system at escape velocity, departing on trajectories that never bring them back. We know our own solar system does this, because we can see the evidence. The Oumuamua cloud, a vast, spherical halo of icy bodies at the outermost edge of the solar system, extending perhaps halfway to the nearest star, is thought to be largely composed of material that formed closer to the Sun and was gravitationally ejected outward by Jupiter and the other giant planets during the tumultuous early history of the solar system. These are objects that our solar system threw away. Objects that began their lives near the Sun and ended up billions of miles out, in the dark, in a cloud so distant and diffuse that individual members of it are nearly impossible to detect. If our solar system has this ejection history, and we know it does, then every other star system in the galaxy that forms planets almost certainly does too. The physics of planetary formation is not unique to us. Across the Milky Way, across billions of star systems, the same process has been playing out for billions of years. Planets form. Material gets flung outward. Some of that material escapes into interstellar space, which means interstellar space should be populated, threaded with debris from a billion different planetary formation events. Rocks and ice and fragments of other worlds, of other solar systems, moving through the dark between the stars on journeys that began long before anything lived on Earth. The models gave astronomers estimates of how often one of these objects should pass through our solar system. The numbers varied depending on assumptions about ejection rates and object sizes, but the consensus was something like: a detectable interstellar visitor should transit our solar system roughly once per decade, maybe more often if the objects are smaller than we tend to think, maybe less often if planetary formation is more efficient at holding onto its material. The prediction was there. It had been there for years. Astronomers even had a name ready for such objects before any had been found. Interstellar objects, marked in catalog systems with a specific designation. They were anticipated, they were theorized, they just hadn't been seen yet. So when Oumuamua appeared, the initial reaction within the astronomical community was an alarm. It was wonder, genuine, excited, historically significant wonder, but not alarm. The name given to it, Oumuamua, comes from the Hawaiian language, contributed by researchers at the Institute for Astronomy at the University of Hawaii, in recognition of the fact that the Pan-STARRS telescope on Haleakala had made the discovery. The name is often translated roughly as scout or a messenger from afar arriving first, and carries a connotation of something that precedes a larger group. It was a fitting name, in retrospect, because in some sense, Oumuamua arrived before our understanding of what such visitors could be. But wonder and alarm are different things. And, for the first few days, this was wonder. Think of it this way. Imagine you live in a city, and someone tells you, based on careful statistical reasoning, that a traveler from a foreign country should pass through your neighborhood about once every decade. And then, one afternoon, you look out your window and see a figure walking down your street who's clearly from somewhere very far away. The clothing is different. The gait is different. Everything about them signals that they didn't start their journey anywhere nearby. You're curious, you want to know more, but you're not frightened, and you're not confused, because you were told this would happen. That was the initial posture toward Oumuamua. We were told interstellar visitors were coming, one arrived, let's look at it, and so they did. In the days and weeks following Werek's detection, telescopes across the world and in space turned toward Oumuamua's retreating path. The Hubble Space Telescope, our most capable orbiting observatory, gathered light from it. The Spitzer Space Telescope, which observes in infrared, looked for its heat signature. Ground-based observatories in Chile, in the Canary Islands, at facilities run by the European Southern Observatory, all contributed observations. The very large telescope in the Atacama Desert added to the dataset. Oumuamua had already made its closest approach to the Sun, called perihelion, on September 9, 2017, about 6 weeks before Werek spotted it. It was on the outbound leg of its trajectory when detected, already putting distance between itself and the Sun at an impressive speed. The detection came late, not because the instruments were inadequate, but because no survey in 2017 was specifically designed to catch objects moving this fast on hyperbolic trajectories. Pan-STARRS caught it almost by accident in the normal course of its wide-field sky survey. But late or not, there was still time to gather data, and gather it they did. The first round of observations confirmed the hyperbolic trajectory, no question. This was an interstellar visitor. The orbital parameters left no doubt. And the initial spectral observations, looking at what colors of light the object reflected, were consistent with a reddish, rocky surface, similar in color to objects found in the outer reaches of our own solar system. Nothing exotic there, just a reddish rock. The size estimates suggested it was somewhere between 100 and 1,000 meters in its longest dimension, so ranging from the length of a football field to nearly a kilometer. Modest for an asteroid, not unusual for an interstellar visitor in the models. At this point, the story seemed to be heading toward a clean resolution. Interstellar object detected. Confirmed hyperbolic trajectory, rocky surface, consistent with expectations, remarkable, certainly historic, even, but not mysterious. And then came the trajectory refinement. Under normal conditions, under the conditions governed by gravity alone, the path of a small body through the solar system is extraordinarily predictable. Newtonian gravity is one of the most rigorously tested laws in all of science. We can predict the position of a comet decades in advance with precision, down to fractions of an arcsecond. We account for every gravitational perturbation, Jupiter's pull, Saturn's influence, the subtle gravitational effects of every planet in the solar system, and arrive at predictions that match observations with astonishing accuracy. When the teams working on Oumuamua's trajectory used all of those gravitational influences to calculate where the object should be, when they ran the models and compared the predictions to the observations across the full set of telescopic measurements, the numbers didn't match. Not by a lot, but they didn't match. Oumuamua was ahead of where gravity predicted it should be. It was moving slightly faster than gravity alone could account for. The deviation was small but consistent across multiple observations by multiple independent telescopes, and it was growing. The gap between predicted and observed positions was widening in a way that was systematic, not random. Something was accelerating Oumuamua beyond what gravity could explain. The paper, documenting this formally, published in Nature in June 2018, led by Marco Micheli at the European Space Agency, with a co-author list that read like a who's who of solar system dynamics, was careful and precise in its language. The non-gravitational acceleration, they wrote, was real. It was statistically significant. It could not be explained by any gravitational effect, not from known planets, not from hypothetical unseen masses, not from the tiny relativistic effects that are sometimes relevant for objects moving very fast. Something non-gravitational was pushing Oumuamua. The immediate, obvious, well-established candidate was outgassing. When comets approach the Sun, solar heat penetrates their surface and vaporizes ices trapped just below, water ice, carbon dioxide, carbon monoxide, and other volatile compounds. These gases explode from the surface in jets, and those jets act like small rocket thrusters. The effect is well documented. It's why comets have tails. The tail is actually the expelled material being pushed away from the Sun by solar radiation, and the thrust from outgassing can produce measurable deviations from a purely gravitational trajectory. We've observed and modeled this effect extensively. It's not exotic. It's basic comet physics. So, when the trajectory data showed non-gravitational acceleration, the first thing every astronomer in the field thought was outgassing. The problem was the evidence for it, or, more precisely, the devastating, thorough, exhaustive absence of evidence for it. Here's why that matters so much. When a comet outgasses, the process is not silent. The gases that burst from a comet's surface interact with sunlight in characteristic ways. Each molecule, water, carbon dioxide, carbon monoxide, cyanide, formaldehyde, the whole chemical menu of a typical comet, absorbs and re-emits specific wavelengths of light. These spectral signatures are like fingerprints. When astronomers split the light from a comet into its component colors, the same process a prism uses to make a rainbow from white light, those molecular fingerprints are readable, unmistakable. We've been reading them for well over a century. Outgassing also produces a physical cloud around the object, a coma. The diffuse halo of gas and dust that gives comets their characteristic appearance, and that can extend for millions of kilometers in both directions. A coma at Oumuamua's distance from the Sun would have been detectable, and then there's the thermal signature. The Spitzer Space Telescope was designed specifically to observe in infrared wavelengths. Any object near the Sun absorbs sunlight and re-emits it as heat, a thermal signature that Spitzer was ideally suited to detect. Active outgassing on a comet produces additional thermal emission beyond the simple heating of the surface. Spitzer would have seen it. The Spitzer didn't detect Oumuamua at all. Not a thermal signature, not a coma, not a spectral fingerprint of any volatile compound. 3 different detection methods, each sensitive and well-proven, looking for the evidence that outgassing would have left, and finding nothing. The team that documented the non-gravitational acceleration had considered this. They'd tried to make the outgassing model work. You can construct a scenario in which a comet outgasses very specifically, in ways that produce the necessary thrust, without producing detectable signatures at the sensitivity levels of the instruments used. But those scenarios require special conditions, very specific ejection geometries, very specific compositions, very specific orientations. And even under the most favorable assumptions, some trace should be visible. There was no trace. The data from 3 independent telescopes, Hubble, Spitzer, and ground-based spectroscopy, formed a wall of negative results that the outgassing hypothesis couldn't climb. Someone checked the instruments twice, then a third time, the anomaly held, and that is the moment this story changes character. Because, when the most obvious explanation fails, when the answer you reach for first doesn't fit the evidence, you don't walk away. You ask what else could possibly explain what you're seeing. You keep every question open that you can't yet close. If this had been the only strange thing about Oumuamua, If the acceleration had arrived with no accompanying mysteries, if everything else about the object had been perfectly normal, the scientific community might have absorbed it as an unusual case, an object with some exotic property that behaved differently from expectations, but ultimately classifiable once the right composition was identified or the right mechanism was understood. Science encounters phenomena at the edge of its categories regularly. It adjusts, it moves on, but the acceleration was not the only strange thing about Oumuamua, not by a long way. Because, once scientists started examining the other data, the brightness measurements over time, the light curve that tracked how the object's apparent luminosity fluctuated as it rotated, a second layer of the mystery emerged. And what they found in that light curve made the acceleration look, if anything, like the simpler problem, because the second layer wasn't about what Oumuamua did. It was about what it was, and that, it turned out, was unlike anything we had ever seen before. Chapter 3a. The shape that should not exist. Let's talk about how astronomers figure out the shape of an object they can never actually photograph. Oumuamua, at its closest, was tens of millions of miles away. No telescope we have can resolve it into a visible disk. To every instrument that looked at it, it was a point of light, a dot. So, how do you figure out what shape a dot is? You watch how it blinks. As Oumuamua tumbled through space, rotating, the way most small bodies do, its brightness changed. When one of its faces was turned toward us, more light reflected toward Earth, and it appeared brighter. When it rotated to present a narrower profile, it appeared dimmer. By tracking these fluctuations in brightness over time, astronomers can build what's called a light curve, a record of how the object's apparent brightness changes, and from that curve, they can infer things about the object's shape, rotation period, and how elongated it is. The light curve for Oumuamua was extraordinary. The brightness variation they measured was roughly 10 to 1. At its brightest, Oumuamua reflected approximately 10 times as much light as it did at its dimmest. That number seems abstract until you compare it to what we normally see. A typical asteroid, tumbling in space, might show brightness variations of 2 or 3 to 1. Maybe 4 to 1 for an unusually elongated object. The physics of reflected light puts constraints on how much variation is possible for a given shape. A perfect sphere wouldn't vary at all. A slightly flattened sphere varies a little. A cigar-shaped object varies more. To produce a 10 to 1 brightness variation, an object has to be dramatically elongated. We're talking about aspect ratios, length to width, somewhere between 5 to 1 and 10 to 1. Imagine a cucumber. Now stretch it until it's the length of a school bus, but the width of a dinner plate. That's the geometry implied by the data. Some models suggested it might be even more extreme, more like a thin, flat disk, like a cosmic frisbee, than a cigar. No known asteroid or comet in our solar system comes close to those proportions. Natural objects form the way they do through collisions, accretion, the physics of gravity pulling material together. Those processes tend to produce shapes that are, in the grand scheme of things, relatively compact. Irregular, yes, sometimes elongated, certainly, but not like this. The natural question, and it's a legitimate one, is whether the light curve measurements are accurate. Could something about the data be misleading? Astronomers considered this. Multiple independent datasets from different telescopes were compared. The brightness variation was consistent. It wasn't an artifact of the instruments or an error in the reduction pipeline. Oumuamua was genuinely shaped, unlike anything we had seen before, and here's where the first open loop begins to close. Remember the acceleration, the thing we couldn't explain without gassing. There's another mechanism that can accelerate an object in space without leaving any chemical trace: solar radiation pressure. Sunlight isn't just light. It carries momentum. When photons, packets of light, hit a surface and bounce off, they transfer a tiny push to whatever they hit. For large objects like planets, this pressure is utterly negligible compared to gravity, but for small, thin objects, objects with a high surface area to mass ratio, it can add up to a measurable force. A spacecraft can be driven by solar sails. The concept is well established in physics and has even been tested in small-scale missions. A thin, reflective sheet deployed in sunlight will experience a gentle but real push from the pressure of the photons hitting it. If Oumuamua was extremely thin, if it had an enormous surface area relative to its mass, solar radiation pressure alone could explain the observed acceleration. No gases needed, no chemical signature, just sunlight pushing on a sail-like surface. This is not speculation, the mathematics works out, researchers checked the numbers. If Oumuamua's density was low enough, and its cross-sectional area was large enough, radiation pressure from the sun could produce exactly the non-gravitational acceleration that was observed. But for the math to work, the object had to be extraordinarily thin. Thinner than any natural object we have ever catalogued, so now we have two anomalies that are potentially linked. An extreme shape, an acceleration that the extreme shape might explain, but only if the object is thin to a degree that no known natural process reliably produces. One anomaly can be a fluke, a measurement artifact, an unusual formation event, something at the edge of the natural distribution. But two that are connected to each other in a way that deepens both of them, that's harder to wave away. And if that had been all, if scientists had stopped there, with an unusually shaped object that accelerated in a way consistent with its unusual shape, they might have written it off as an exotic but ultimately natural object outside the range of what we'd previously catalogued. Unusual but explainable in principle, but it wasn't. Chapter 3b. When three data points stop being a coincidence. Before we get to the third piece of evidence, let's briefly pause on something that's easy to miss in the mainstream coverage. Something that was quietly noted in the scientific literature, and then largely passed over in popular accounts. Because it adds a dimension to this story that most people who have heard of Oumuamua don't know about. When Oumuamua was detected, scientists did what they routinely do with any unusual solar system object. They traced its trajectory backward. This is standard procedure. Using the same orbital mechanics that allow us to predict exactly where a comet will be 6 months from now. You can run the math in reverse, accounting for the gravitational influence of every planet, adjusting for the perturbations introduced by each one as the object's path is rewound through time, until you arrive at a point of origin outside the solar system. For a true interstellar visitor, the expectation is that this backward traced path would point toward a specific nearby star, or at least toward a region of sky where a likely parent system might reside. Maybe the object was ejected from one of the dozen or so stellar systems within about 10 light-years of the Sun. Maybe from a system that was somewhat closer to ours in the distant past, before the star's individual motions through the galaxy pulled them apart. Either way, you'd expect a trajectory that could plausibly be connected to a stellar source. Astronomers did the calculation, several teams, independently, using the full dataset. Oumuamua's backward trajectory didn't point toward any known nearby star. More specifically, the object appeared to come from a direction of space that is, in technical terms, at rest relative to the local standard of rest. The local standard of rest is a reference frame defined by the average velocity of all the nearby stars in our galactic neighborhood. Essentially, the consensus motion of the local stellar population. Most stars in the solar neighborhood are moving relative to this frame. because they have their own individual velocities acquired during their formation or through gravitational interactions over billions of years. Oumuamua's pre-encounter velocity placed it very close to this standard of rest, not moving with any specific star, not moving much at all relative to the local background. This is statistically unusual in a specific way. Think of it like this. Stars in our galactic neighborhood are like ships on an ocean, each moving at its own speed and heading. If you eject a piece of debris from one of those ships, the debris initially moves with the ship, carrying its velocity. Over time, if nothing acts on the debris, it continues in the same direction at the same speed. So, a random piece of interstellar debris ejected from a star system should be moving more or less in the same direction and at the same speed as the star that ejected it. An object that is essentially stationary relative to the average of all local stars, like Oumuamua, is unusual in this context. The most natural interpretation is that either it has been traveling for so long that the star which ejected it has moved far away, leaving the debris behind in something close to the galactic reference frame, or it experienced something that altered its velocity over its interstellar journey, or its kinematic history is simply different from what we'd expect of a standard planetary ejection event. This detail received very little press coverage. It appeared in the scientific papers, it was noted by researchers, and then it was largely swept under the rug as the more dramatic anomalies. The shape, the acceleration, dominated the public conversation. But it's a third data point that doesn't fit the standard picture. Now let's get to what crystallized everything. In August 2019, almost 2 years after Oumuamua's detection, when the scientific community was still actively publishing competing hypotheses about what the first interstellar visitor had been, a Crimean amateur astronomer named Gennady Borisov was conducting his own sky survey with a telescope he had built himself. And he found something, a comet, moving on a hyperbolic trajectory, confirmed interstellar. This was Comet Borisov, officially designated 2I/Borisov, the 2I, indicating it was the second identified interstellar object, and it became, in the context of the Oumuamua debate, one of the most scientifically useful discoveries in recent memory. Because Borisov was perfectly normal, not marginally normal, not normal with some caveats, beautifully, thoroughly, unreservedly normal. It had a coma, the cloud of gas and dust that surrounds an active comet as solar heat vaporizes its surface ices. Its spectrum showed clear signatures of water vapor, carbon monoxide, and diatomic carbon. The classic chemical fingerprints of a comet doing exactly what comets do. Its brightness was consistent with a nucleus of roughly half a kilometer, well within the range of known solar system comets. Its light curve showed modest brightness variations consistent with an ordinary compact shape. Borisov, in short, looked precisely like what our models predicted an interstellar comet should look like. It confirmed that interstellar objects can be ordinary, that the process of planetary formation produces debris that gets ejected into interstellar space, travels between stars, and eventually passes through other systems, and that this debris, at least sometimes, is just what you'd expect. An icy, outgassing, totally unremarkable comet. For the scientists who had been wrestling with Oumuamua, Borisov was deeply useful in a way that cut in two directions simultaneously. On one hand, it was a relief. It demonstrated that interstellar objects exist, can be detected, and can match predictions. Our theoretical framework wasn't completely broken. The models that predicted interstellar comets turned out to be right, at least about Borisov. On the other hand, the contrast it provided made Oumuamua's anomalies dramatically sharper. You couldn't, after Borisov, argue that Oumuamua's lack of outgassing was just what interstellar objects do. Because here was an interstellar object, and it outgassed exactly as expected. You couldn't argue that Oumuamua's unusual shape was just what interstellar objects look like. Because here was an interstellar object with a perfectly ordinary shape. Borisov gave science a control sample of 1, a comparison point, and when you set the two interstellar visitors side by side and look at them together, Oumuamua stops being unusual in some vague, general sense and becomes unusual in a specific, pointed, hard-to-explain sense. Borisov outgassed. Oumuamua didn't. Borisov had an ordinary shape. Oumuamua didn't. Borisov's backward trajectory pointed plausibly toward a parent star system. Oumuamua's didn't. Borisov behaved the way our models said it should. Oumuamua didn't. Every property of Borisov that confirmed our models was, simultaneously, a property that Oumuamua lacked. And this is where the internal scientific debate, which had been developing in the journals since 2018, began to take on a more urgent character. Some researchers held firmly to the conservative position. Oumuamua is a natural object. We simply haven't encountered this particular class of natural object before, because we've never had the detection capability to find interstellar visitors until now. The sample size is 2. That's not enough to make strong statistical claims about what interstellar objects should look like. Oumuamua might be unusual among interstellar visitors, the same way that some asteroids in our own solar system are unusual among asteroids. Outliers exist in any population. This position is scientifically defensible. It's the epistemically cautious position. It requires the fewest new assumptions. Others, not fringe voices, not science communicators looking for clicks, but researchers at serious institutions publishing in serious journals, looked at the growing catalog of Oumuamua's properties and raised a different concern. At some point, they argued, the number of independent anomalies stops being a list of individual puzzles and starts being a coherent signal. When a single object deviates from expectations in multiple independent ways, and when those deviations all point in a consistent direction, toward an object that is thin, low density, and driven by radiation pressure rather than gravity or outgassing. The most honest response is to acknowledge that the object is genuinely anomalous, not just different. 1 anomaly can be dismissed, 2 can be coincidence, 3 is a pattern. And this pattern, the shape, the acceleration, the kinematic origin, the total absence of any chemical or thermal signature, was pointing somewhere. Patterns demand explanations. And the explanations available were increasingly uncomfortable. But before we sit with those interpretations, and we will, in detail, in the next chapter, there's one more dimension of this story that needs to be placed on the table. Because the implications of Oumuamua, whatever it turns out to have been, extend far beyond the object itself. They extend to what it suggests about the universe we live in. And that is a larger and stranger question than any of the ones we've covered so far. Chapter 3. See what Oumuamua says about everything else. Here's a number that should give you pause. Before Oumuamua, the theoretical models of planetary formation and interstellar debris predicted a specific density of interstellar objects passing through the solar system. These models were built from what we understood about how planets form, how much material gets ejected in the process, and how that ejected material spreads across the galaxy over cosmic timescales. Different research groups ran different versions of these calculations and arrived at somewhat different numbers, but the general consensus settled around one detectable interstellar object passing through the inner solar system per decade, give or take. Pan-STARRS found Oumuamua in its first year of operation at the sensitivity required to detect such objects. That's broadly consistent with the 1 per decade prediction, so on the surface, everything seems fine. But then you ask a different question. If Oumuamua is a member of a class of objects, thin, low density, driven by solar radiation pressure, how many such objects need to exist in interstellar space to make it statistically likely that one would pass through our system and be found in the first viable survey year? The answer, the model's return, is troubling. For objects with Oumuamua's properties to appear at that rate, the number density of such objects in interstellar space would have to be orders of magnitude higher than standard planetary formation models predict. Not twice as high, not 10 times as high. The estimates, depending on how you handle the object's assumed size and detection efficiency, run into the hundreds of times higher than the models expect. Planetary formation is not an infinitely efficient ejection machine. The amount of debris that a forming solar system throws into interstellar space is constrained by the mass of the protoplanetary disk, the efficiency of the planet-building process, and the dynamics of the young planetary system. Our solar system, and star systems like ours, simply don't have enough material to account for the density of Oumuamua-like objects that the detection statistics imply. If we take those statistics seriously, this is what drove some researchers toward more exotic explanations, not a desire for drama, a straightforward accounting problem in the models. If Oumuamua-like objects are genuinely abundant enough to explain our detection, where do they all come from? One possibility is that our models of planetary formation are significantly wrong in the direction of underestimating how much material gets ejected. Perhaps early stellar systems are far more violent, far more prolific in their debris production than current simulations suggest. Perhaps there are formation environments, systems with unusually massive disks, unusually dynamic giant planets, unusually close stellar encounters that produce vastly more interstellar debris than we've accounted for. Another possibility is that thin, low-density objects of this type are formed not during planetary formation, but by a different process entirely, perhaps by collisions between objects in interstellar space, perhaps by some mechanism we haven't identified yet. The universe has a long history of producing phenomena through mechanisms that took humans a long time to figure out. A third possibility, which has been proposed in the literature and which I'll address directly, is that some fraction of what Oumuamua represents is not natural in origin. We'll get to that in the next chapter. For now, let's stay with the physics. Let's talk about the interstellar radiation field. Between stars, space is not completely dark. It's threaded with the light of every star in the galaxy. A diffuse, omnidirectional background of photons contributed by hundreds of billions of stellar sources. This interstellar radiation field is weak by any standard we'd apply near a star, but it is constant and omnipresent. And, for an object with an extremely low surface density, the kind of surface density required by the radiation pressure hypothesis for Oumuamua, it matters. A dense asteroid, traveling through interstellar space for millions of years, is essentially unaffected by the interstellar radiation field. The photon pressure is far too weak, relative to the object's mass, to matter. But for an object with Oumuamua's implied surface density, a thin, flat structure with an enormous area relative to its mass, the cumulative push of billions of years of interstellar photon pressure could meaningfully alter its trajectory and velocity, slowly, almost imperceptibly by human standards, but steadily. This has an interesting implication for the kinematic anomaly we discussed in Chapter 3b. The fact that Oumuamua appeared to be nearly at rest relative to the local standard of rest, a thin object, pushed continuously by the omnidirectional interstellar radiation field over an extremely long journey, might naturally settle toward a velocity that approximates the median of the radiation field's source stars. The steady, diffuse push from all directions might, over geological timescales, drive such an object toward a sort of kinematic equilibrium, near the local standard of rest. This is a speculative but publishable connection. It's the kind of insight that makes a hypothesis interesting rather than arbitrary. When different anomalies begin to explain each other through a coherent physical mechanism, that's a sign you might be onto something. Whether that something is a new class of natural object or something else entirely, the coherence of the picture is worth noting. Now, let's talk about what's coming that will actually test these ideas. The Vera Rubin Observatory in Chile began its legacy survey of space and time, the LSST, in 2025. This instrument is, in the context of this story, perhaps the most important piece of hardware humanity has ever built for addressing the Oumuamua problem. Not because it was designed specifically for this. It was designed as a general-purpose wide-field survey telescope that would image the entire southern sky every few days to depths far beyond what pan-stars can achieve. But the combination of its sensitivity, its field of view, and its survey cadence means it will find interstellar objects, many of them, regularly, in a way that no previous survey could. Current projections suggest Vera Rubin will identify somewhere between 1 and a dozen interstellar visitors per year over the course of its planned 10-year survey. That's a statistical sample large enough to say something meaningful about the population of objects that move between the stars. The critical question it will answer: are objects with Oumuamua-like properties common or rare? If Vera Rubin starts finding thin, radiation pressure-accelerated objects regularly, if it begins building a catalog of objects with unusual shapes and non-outgassing acceleration, then we have a new class of natural object that the scientific community will need to explain and model. That would be an extraordinary finding, but an ultimately comprehensible one. Unusual objects, once they appear in sufficient numbers, get explained eventually. Physical processes get identified. Formation mechanisms get proposed and tested. If, instead, Vera Rubin finds only Borisov-like objects, active comets with chemical signatures, ordinary shapes, predictable trajectories, and nothing that resembles Oumuamua, then Oumuamua's uniqueness becomes statistical fact. A 1 in a billion outlier. Something that formed or arrived through a mechanism so rare it has produced only one detectable example in the history of human observation. And that, too, demands a different kind of explanation. Either outcome advances the science dramatically. Either outcome makes what Oumuamua was, or is, a more answerable question than it is today. We are, right now, at the beginning of the era in which these questions become empirically testable. That's not a small thing. For most of human history, questions about what moves between the stars were purely theoretical. They had to be. We had no instruments capable of detecting interstellar visitors, even in principle. Pan-stars found the first one by accident. Vera Rubin is looking for them on purpose. Whatever it finds, the story of Oumuamua will be a different story once those results are in. Either it will be the pioneering specimen of a known and catalogued class of interstellar object, or it will remain, uniquely and permanently, the one thing we found that we couldn't fully explain. Both of those endings are extraordinary, only one of them is more comfortable than the other. Chapter 3D, 3 interpretations, and the one no one wants to say out loud. Let's be careful here, because this is the part of the story where popular coverage tends to go in one of two directions. Either everything gets explained away in neat, tidy scientific language that papers over the real uncertainties, or everything gets thrown into the realm of wild speculation that abandons the scientific framework entirely. Neither of those serves you. What we're going to do instead is lay out the interpretations that are actually present in the scientific literature. ranked from most conservative to most provocative, with an honest accounting of what supports each one and where each one fails. The first interpretation, the conservative one, is that Oumuamua is an exotic natural object of a type we haven't previously catalogued. The sub-hypotheses within this category include several specific proposals. Daryl Seligman and Jane Liu, both serious and credentialed astronomers, proposed that Oumuamua might be a fragment of a hydrogen iceberg. Molecular hydrogen ice, in theory, could vaporize in sunlight without leaving a detectable spectroscopic trace. Because hydrogen ice is nearly invisible to the instruments we used, the sublimation of hydrogen gas could, in principle, provide the observed acceleration without the chemical signatures we'd normally look for. The hypothesis is clever, and it fits some of the data. The problem is that hydrogen icebergs are not expected to survive the interstellar journey. Cosmic radiation and the diffuse heat of interstellar space would destroy a hydrogen ice object long before it could travel from another star system to ours. Multiple independent analyses of the survivability question came back with the same answer. It doesn't hold up over the distances involved. A related proposal involved nitrogen ice, a fragment of a Pluto-like object's surface, knocked loose by a collision in another system and sent tumbling through interstellar space. Nitrogen ice is slightly more robust than hydrogen ice. It would outgas very slowly, and the spectroscopic signature of nitrogen is difficult to detect with our instruments. This hypothesis was taken more seriously. But the surface density required, the mass-to-area ratio implied by radiation pressure as the acceleration mechanism, still pushes into territory that's extremely difficult to produce naturally. Nitrogen ice, even in thin sheets, would need to be structured in ways that currently have no known natural formation pathway. The second interpretation, moderate, is that Oumuamua represents a genuinely new class of interstellar material. Not a specific composition, but a structural category. Ultra-low-density fractal aggregates, sometimes called fluffy objects in the literature. Think of a snowflake compared to a ball of snow. The snowflake has much lower density because it's mostly empty space arranged in a regular pattern. If Oumuamua was a kind of cosmic fractal structure, a loosely assembled aggregate with an enormous surface area and very little mass, it could be driven by radiation pressure without requiring any unusual chemistry. Its shape would be natural in the way that a snowflake's shape is natural, generated by the physics of how material clumps together under certain conditions. This interpretation has the advantage of fitting the data without requiring any single unusual material. The challenge is that it requires a formation mechanism we haven't directly observed, and the structural integrity of such an object over a long interstellar journey is uncertain. Then, there's the third interpretation. Avi Loeb, the chair of Harvard's astronomy department, published a paper in 2018, and subsequently a book, arguing that the simplest explanation for Oumuamua's properties is that it is, or was, a light sail, an artificially constructed thin membrane designed to be pushed by stellar radiation. The same technology concept that human engineers have been developing for decades, scaled up. The reaction to this proposal in the scientific community was mixed, to put it gently. On the one hand, Loeb is not a fringe figure, he's a prolific researcher with real credentials. The mathematics in his paper is correct. The properties required for a light sail that behaves the way Oumuamua did are physically consistent with what was observed. The proposal was published in Astrophysical Journal Letters, which is a peer-reviewed journal with real standards. On the other hand, extraordinary claims require extraordinary evidence, and the evidence for the light sail hypothesis is entirely indirect. It's a properties match. Oumuamua's observed characteristics are consistent with a light sail, but many things can be consistent with a description without being what the description implies. The absence of a better natural explanation is not, by itself, evidence for an artificial one. The scientific community has not endorsed Loeb's hypothesis, but it has also, critically, not falsified it. And here's what I want you to sit with for a moment, not the alien question, because that's almost the wrong question, but something slightly different. Why is it that when a scientist of Loeb's standing uses the word artificial in a published paper, the immediate response from much of the scientific community is discomfort? That discomfort is worth examining. Part of it is legitimate scientific caution. We've been burned before by premature claims of signals or structures that turned out to be natural phenomena. The history of SETI is littered with detections that looked artificial and weren't. The prior probability of encountering something artificial is, by any reasonable calculation, very low. But part of the discomfort, I think, is something else. Something more human. We are deeply invested in having explanations. The unknown is uncomfortable. When a phenomenon doesn't fit our models, the instinct is to adjust the phenomenon, to find a way to categorize it, to smooth it into something familiar, rather than to genuinely hold open the possibility that we don't have the right model yet. Oumuamua forces a kind of honesty that's not easy. It says, here is something we measured, carefully, repeatedly, rigorously, and we don't fully understand it, not, we'll figure it out soon, and not, it's almost certainly this one thing, we just need to confirm it, we don't fully understand it. That kind of admission lives uncomfortably in a culture, scientific culture and popular culture alike, that prizes answers over questions. But science, at its best, has always grown not from the accumulation of certainties, but from the honest acknowledgement of gaps. Oumuamua is a gap with a name. And so, after all of this evidence, the shape, the acceleration, the origin trajectory, the absence of outgassing, the contrast with Borisov, the structural challenges to planetary formation models. The question is no longer whether something strange happened. The question is, what does that strangeness really mean? Remember what we asked at the beginning. Why does Oumuamua accelerate without leaving a trace? We've been building toward that question for this entire video, laying in the evidence, one layer at a time, the shape, the trajectory, the contrast with Borisov, the models that can't fully account for it. After everything we've seen, here's where we stand. We know the acceleration is real. We know outgassing didn't cause it. We know the object's shape is unlike anything naturally catalogued. And we know the scientific community is actively, genuinely divided on what combination of natural explanations, if any, can account for all of it together. What we're going to do now is go deeper than the headlines, into the parts of this story that popular science coverage consistently underreports. Because these are the parts that require sitting with discomfort rather than moving briskly toward resolution. The mainstream press, and even much of the popular science coverage, presented Oumuamua as a strange but probably natural object that science was close to explaining. The coverage of the hydrogen iceberg hypothesis, for example, tended to treat it as a near solution. Scientists think they may know what Oumuamua is. That kind of headline, satisfying, reassuring, implying that the mystery had been contained. What those headlines didn't convey was what was actually happening in the technical literature. Read the papers, not the abstracts, the papers, and a different picture emerges. Multiple studies in Nature Astronomy, Astrophysical Journal, and Astrophysical Journal letters over the years 2018 through 2024 addressed specific quantitative constraints on Oumuamua's properties. These constraints were, in several cases, mutually incompatible with the proposed natural explanations. Here's one example that illustrates the problem clearly. The Spitzer Space Telescope observed Oumuamua in thermal infrared, which is to say, it looked for the heat signature of the object itself. Any object in the inner solar system absorbs sunlight and re-emits that energy as heat. The amount of heat emitted scales with the object's size. A larger object presents more surface area to the sun, absorbs more energy, and radiates more heat. Spitzer is exquisitely sensitive to this kind of emission. It was designed for exactly this kind of work. Spitzer didn't detect Oumuamua at all. That non-detection is actually informative in a very specific way. It puts a hard upper limit on the object's size. A certain amount of thermal emission is expected, based on how much sunlight an object of a given size would absorb at Oumuamua's distance from the sun. If Spitzer doesn't see it, the object must be smaller than the threshold at which Spitzer would detect it. The non-detection is not null data. It's a measurement with a result. The object is smaller than this. Now combine that constraint with the shape constraint from the light curve. The factor of 10 brightness variation tells you the object is dramatically elongated or flat, a high aspect ratio, and the Spitzer non-detection tells you the overall size must be below a certain threshold. Put those two constraints together, and you get an object that has to be simultaneously small and extremely elongated or flat. The geometry that satisfies both constraints is, in technical terms, a thin sheet, a flat slab, something with very large area in 2 dimensions and very small extent in the third. Now, add the third constraint. The mass-to-area ratio implied by the radiation pressure calculation. For solar radiation pressure to produce the observed non-gravitational acceleration at Oumuamua's distance from the sun, the mass-to-area ratio must fall below a specific value. Mass per unit area, grams per square centimeter, in the units that matter here, must be below roughly 0.1 grams per square centimeter to make the math work. That's not a guess. That's a calculation with measured acceleration and known solar radiation pressure. 0.1 grams per square centimeter is extraordinarily light. For comparison, a typical sheet of writing paper has a surface density of about 8 to 10 grams per square centimeter. Oumuamua would need to be roughly 80 to 100 times less dense per unit area than a piece of paper. Lighter than any naturally occurring thin material we've catalogued, at the boundary of what known materials, even manufactured ones, can achieve. This is what the papers say, not, it's strange. They say, the combination of measured properties, taken together, subjected to rigorous quantitative analysis, does not fit comfortably within the parameter space of known natural objects, and, in some cases, the hydrogen iceberg hypothesis being the most prominent example, researchers have demonstrated that the proposed explanation is not just a poor fit, but physically impossible over interstellar travel distances, because the material simply wouldn't survive. Hydrogen ice is extremely fragile in the interstellar environment. The diffuse radiation field between stars, even weak radiation, would destroy a hydrogen ice object long before it could travel from another star system to ours. Multiple independent analyses from teams with no particular stake in any particular outcome arrived at the same conclusion. The hydrogen iceberg proposal doesn't survive the survival problem. The ice doesn't survive the journey required for the object to reach our solar system from another star. The nitrogen ice hypothesis fares somewhat better on this particular point. Nitrogen ice is more robust, but it introduces its own structural problem. Thin sheets of nitrogen ice with the mechanical properties required to match the observed data, holding together during an interstellar journey, remaining structurally intact while being driven by radiation pressure, surviving the tidal stresses of a near-solar passage, have no confirmed formation mechanism in known planetary system physics. And here's what almost never appears in the popular coverage. There is a quiet but genuine debate within the astronomical community about whether the impulse to find a natural explanation has, in some cases, led to the parameters of proposed explanations being stretched beyond what the evidence genuinely supports. This debate happens in the polite language of academic disagreement, responses and counter-responses, comments and replies in the journals, but it's real. The impulse to contain an anomaly within existing frameworks is normal and often productive. Sometimes the framework just needs to be adjusted. Sometimes it needs to be replaced. What the papers, read carefully, actually say is not, "We know what it was." They say, "Here are the options available, here are the constraints each one must satisfy, and here is the fact that none of them satisfies all the constraints without requiring something we've never directly observed." That's the honest summary of where the scientific literature stands. That's a different story than the one the headlines told. Now, let's talk about where things stand as of the most recent published research. In 2019, as mentioned, Borisov arrived and behaved exactly as expected. That contrast was enormously useful, not just scientifically, but rhetorically. It gave the scientific community a reference point. Borisov is what we expected. Oumuamua is what we got instead. In the years since, the theoretical work on Oumuamua has continued, even as the object itself has moved far beyond the reach of any instrument we possess. By now, Oumuamua is somewhere beyond the orbit of Uranus, heading out of the solar system on a trajectory that will take it into interstellar space within a generation. We will never observe it again. What we have is the data from those weeks in 2017 and early 2018 when it was close enough to measure. And researchers have continued to squeeze every drop of information from that data. The Seligman-Laughlin-Loeb debate, a useful shorthand for the broader disagreement in the field, continued in published papers through 2023 and 2024. On one side, proposals that new classes of natural objects could account for Oumuamua's properties with various combinations of unusual composition and structure. On the other, analyses that point out where those proposals break down quantitatively. The field is still genuinely split, not between scientists and cranks, between researchers at Princeton, Harvard, MIT, Caltech, and institutions in Europe, all working with the same dataset and arriving at different interpretations. The Vera Rubin Observatory changes the game. Beginning its full survey operations, it will detect, by current projections, somewhere between 1 and several interstellar objects per year. The baseline question it will answer is, are objects with Oumuamua-like properties common or rare? If Vera Rubin finds many objects that share Oumuamua's unusual shape and radiation pressure behavior, that changes the theoretical conversation. Common things get explained by common processes. A large population of thin, low-density interstellar objects would demand a natural formation mechanism, and it would force the models to find one. If Vera Rubin finds many interstellar objects that look like Borisov, normal, outgassing comets, and nothing that resembles Oumuamua, then Oumuamua's uniqueness is confirmed and deepened. A true statistical outlier requires a different kind of explanation. Either outcome moves the science forward, either outcome is, in its own way, extraordinary. There's one more thing worth raising here, something that almost never appears in popular coverage of this topic. The Project Lyra study. In the years following Oumuamua's detection, a group within the Initiative for Interstellar Studies, a serious organization dedicated to the science of reaching other star systems, conducted a detailed analysis of whether a spacecraft could catch Oumuamua. By the time we knew the object existed, it was already receding. The window for a simple, direct mission had closed. But Project Lyra calculated that a mission using a Jupiter gravity assist, swinging around Jupiter to gain enormous speed, launched in the late 2020s or early 2030s, could theoretically intercept Oumuamua in the 2050s. The delta V required is enormous, at the edge of what current propulsion technology can achieve, but it's not impossible. We won't be sending that mission. The political will and the budget don't exist for it. But the fact that it was seriously calculated, seriously published, tells you something about how the scientific community feels about having let Oumuamua pass without a closer look. We had one chance to study the first interstellar visitor we ever found. We didn't have the detection network in place to find it early enough. By the time we knew it was there, it was already leaving. That's why Vera Rubin matters so much. Next time, and there will be a next time, we want to be ready, and here is what makes all of this truly remarkable. Not Oumuamua itself, not the unusual shape or the unexplained acceleration, not the scientific debate, fascinating as it is. What's remarkable is what the object implies if the natural explanations are correct, any of them. If Oumuamua is natural, if it's a hydrogen iceberg fragment, or a nitrogen ice shard, or a fractal dust aggregate, or some other class of object we've never catalogued, then it represents the first member of a population. There must be others, many others, because we found one on the first survey deep enough to detect them, which means the density in interstellar space has to be significant. Think about what that means. Interstellar space, the vast, dark, cold emptiness between star systems, may not be empty at all. It may be threaded with objects like Oumuamua, thin, lightweight, shaped by processes we don't fully understand, moving between the stars on journeys that began millions or billions of years ago, in planetary systems that may no longer exist, passing through our solar system, silently, without anyone noticing, for 4.5 billion years. Earth has been here for 4.5 billion years, and for all of that time, objects like Oumuamua may have been passing through our solar system, one every decade or every century. We don't yet know the rate, without any form of life on Earth having any idea they were there. Until 17 days in 2017, when we happened to be looking in the right direction at the right moment with an instrument good enough to catch it. Let that sit for a moment. Not a single one. A class. Possibly an abundant class, moving through our cosmic neighborhood, silently, since before Earth had oceans, since before life existed on this planet, threading through the space between the sun and its planets, unseen for eons. We looked up once, and saw, and what we saw, we still haven't fully explained. But there's one more piece to this puzzle, something we haven't touched in this video, something that sits alongside the Oumuamua story in the literature, without quite being part of it yet. Something involving a signal, not from Oumuamua directly, from the region of space it came from. That connection, and what it might or might not mean, that is a story for next time. Tonight, we didn't just learn about a strange object from another star system, we watched science do something it rarely shows the public: struggle, not fail, not give up, struggle. The kind of productive, serious, rigorous struggle that happens when a measurement refuses to cooperate with the models built to contain it. The kind that looks, from the outside, like confusion, but is actually the exact moment science is most alive. When the instruments are working perfectly, the data is clean, the math is sound, and the answer still doesn't come. That's not a failure of science. That's science encountering something genuinely new. Because science doesn't grow from comfort, it grows from exactly these moments, when the data comes back and it doesn't fit. When the first explanation fails, when the second one has problems, when serious people in serious journals use careful language to say, in essence, we're not sure, we don't have this one yet. That's not a breakdown, that's the process working the way it's supposed to. There's something worth sitting with here, beyond the specifics of Oumuamua's shape and trajectory and acceleration. We live in a time when science is often presented as a settled body of knowledge, a library of facts you can look things up in. Textbooks give the impression that the important questions have been answered, and what remains is merely filling in details. Oumuamua is a useful corrective to that impression. The universe does not consult textbooks. It does not organize itself around human categories. It does not slow down to let us catch up. It just is what it is. And occasionally, it sends a messenger to remind us how much of what it is remains outside the boundaries of what we've managed to understand so far. What remains unresolved about Oumuamua is, in some ways, everything. We don't know its composition. We can rule out several things. It probably wasn't standard cometary ice, because the outgassing signatures aren't there. It probably wasn't a solid, dense rock of ordinary asteroid composition, because the surface density required for radiation pressure to explain the acceleration isn't consistent with rock. But we don't know what it was. We don't know the specific mechanism of its acceleration definitively. Radiation pressure is the leading candidate among natural explanations. But that candidate requires a physical structure we've never directly observed in nature. We don't know whether it represents a class of objects or a genuine statistical outlier, whether the interstellar medium is threaded with things like Oumuamua, passing through planetary systems throughout the galaxy, or whether it was a single extraordinary event, unlikely to repeat in any human-relevant timescale. The honest answer to the question, what was Oumuamua, is, we don't know yet, and I want to say this directly, that uncertainty doesn't weaken the story. It's not a gap in the narrative. It's not an unsatisfying ending that needs to be patched over. It strengthens the story, because what we do know is precise and hard-won. The trajectory data is excellent, multiple independent observatories, months of tracking, careful statistical analysis. The light curve data is excellent. The spectroscopic non-detections, the careful, instrument-calibrated searches for outgassing that found nothing, those are excellent data points too. Absence of evidence, when your instrument is sensitive enough to detect the thing you're looking for, is itself evidence. We know, with genuine confidence, what Oumuamua was not. That negative space, that carefully measured absence of everything it should have been, is itself an extraordinary scientific result. It means the universe surprised us, genuinely. Not in a hand-wavy, science is humbling a platitude kind of way, in a specific, quantified, peer-reviewed way. Uncertainty isn't the end of the story, it's the middle of it. There are things this object has taught us that go beyond the object itself. Lessons that apply to how we think about knowledge and the limits of models and what it means to encounter the genuinely new. The first is that small details carry enormous weight. A trajectory deviation measured in fractions of an arcsecond, something that required months of careful observation to detect and had to be separated from dozens of other gravitational influences before it became visible. That tiny detail became the central mystery of one of the most discussed scientific objects in recent memory. A rounding error, essentially, the difference between where an equation said something should be and where the telescope found it. That gap is where this entire story lives. The second lesson is that anomalies are not problems to eliminate. They are invitations. When data contradicts a model, the instinct, the deeply human instinct, even among scientists, is to adjust the data or soften the anomaly. To look for the measurement error. To find the confounding factor, to make the inconvenient number disappear, but anomalies are doing you a favor. They're showing you, precisely and specifically, exactly where your understanding stops. They're pointing at the edge of the map, and the edge of the map is always where the interesting things are. The third is that science is not a library of answers. It's a living record of questions that have been refined, sharpened, and sometimes entirely discarded for better ones. The question we have after Oumuamua, what exists in the space between stars, and how does it get there, is a better question than the one we had before Oumuamua, which was, essentially, no question at all, because we assumed we knew the answer. The fourth is about scale and humility. One object, passing through our solar system in a matter of weeks, 17 days of viable observation, exposed genuine uncertainty in planetary formation theory, in our models of the interstellar medium, in our catalog of what naturally occurs in the universe. One object, and it asked questions that entire communities of scientists are now spending careers trying to answer. The universe doesn't need to be large to surprise us. It just needs to be stranger than our assumptions. And the fifth, perhaps the most important, the deeper we look, the more complex reality becomes. This is not unique to Oumuamua. It is the consistent experience of science across every domain, across every century of inquiry. Every increase in resolution reveals new structure. Every new instrument sees things the old ones couldn't. Every time we think we've mapped the territory turns out to have more rooms. This is not discouraging. It's the best possible news. It means the universe is not exhaustible. It means there will always be more to find. I'll leave you with a few questions I've been turning over since I started going deep on this story. What makes a discovery important, the object itself, or the assumptions it forces you to confront? Because Oumuamua, considered purely as a physical object, is gone. It's billions of miles away and getting farther by the second. You'll never see it. No one will. But the questions it left behind are still here, still open, still appearing in new papers, still shaping the design choices of telescopes not yet built. The discovery outlasted the discoverable object. That's not a common thing. How often do we mistake the familiarity of a category for a genuine understanding of its contents? We've been cataloging asteroids and comets for centuries. We have detailed models of how they form, how they move, how they evolve over time. We teach those models in universities. We use them to design spacecraft missions. And then, one object shows up that fits none of those models, and we're confronted with a simple and slightly uncomfortable truth. The category was real, but our understanding of its outer edges was not as complete as we thought. And this one, what does it feel like to live in a universe that refuses to be finished, that keeps offering new things for new instruments to find? Not frightening. Not unsettling, once you sit with it long enough. There's something that functions like relief in the fact that the universe is still surprising us, that it hasn't run out of questions to ask, that the feeling of discovery, that moment when something appears in the data that shouldn't be there, is still available, still possible, still waiting for the next person looking in the right direction at the right moment. That feeling, I think, is one of the better reasons to keep looking up. If this story stayed with you, if any part of it landed in a way that's still there, a few minutes after it arrived, I'd genuinely like to know which part. Was it the shape? The acceleration? The contrast with Borisov? The model-breaking implications? The quiet discomfort of a gap that hasn't closed? Drop it in the comments. These conversations matter to me, and they shape what comes next on this channel. If you're new to Galaxy Pulse, this is what we do here: long-form stories, real science, the mystery intact. Subscribe if that's the kind of thing worth your time, because we're just getting started. I'll see you in the next one. The object was strange, but what it revealed about the edges of our understanding may be stranger still.